Hello everyone! In this video, we will continue to examine topic 7.3, the structure of matter, and Feynman diagrams with a particular focus on the weak interaction. Alright, this next little topic is so important that I've given it its own video. And this has to do with the fact that in using Feynman diagrams to analyze weak interactions, there is a particular weak interaction that appears over and over and over again in the IB that is important to get right and be familiar with. It shows up on most IB exams in one form or another, and the odds are pretty good that if they ask you to draw a Feynman diagram, rather than simply fill in some results, it'll be for pair production, annihilation, which we've already gone over, or it will be for beta decay. So in representing beta decay with a Feynman diagram, there are a number of different ways to do it. And I've shown sort of my favorite here. But the reason there are a number of different ways to do it is, if you recall, beta decay, and in particular beta minus decay, involves a neutron transmuting into a proton, an electron, and an anti-electron neutrino. This is something you had to memorize in topic 7.1, but now we have the ability to explain what is going on and how. Now, the reason there are a number of different ways of representing this is that fundamentally, the neutron and the proton are hadrons and made up of constituent quarks. Moreover, the two of the constituent quarks do not change. A proton is an up-up-down, and a neutron is an up-down-down. And so the up, or one of the ups and one of the downs will always stay the same in an interaction. As a result, you can either draw a beta decay occurring between the fundamental nucleons, right, the neutron and the proton that occurs in this equation, or you can draw it in terms of the quarks and the quark composition. And if you draw it in terms of the quarks, you're sort of illustrating that one of the quarks is transmuting and the other two are staying the same. This is my preferred representation because you get to do both. But you will see just the quarks or just the hadrons as well. All right, so what happens? Well, beta decay is a multi-step interaction. It involves two vertices in some order. In this particular case, we have a down quark, first emitting a W minus boson. Note that to conserve charge at this vertex, that down quark becomes the up quark that we needed to become. And now we have a W minus boson. And the W minus boson then undergoes... I won't call it pair production, but becomes an electron and an anti-electron neutrino. Now, take a look at this particular interaction here. When it does so, notice that the anti-electron neutrino has an arrow going in because it is an antimatter particle, and the electron has an arrow going out because it is a matter particle, just as it must. This allows it to conserve the lepton number. So lepton number here, there is 0 lepton number coming in. W minus has a 0 lepton number. The electron has a +1 lepton number, and the anti-electron neutrino has a -1 lepton number. So it conserves lepton number. It also conserves charge. Notice this W minus boson has -1 charge, and therefore the sum of these two must also have -1 charge. And in fact, the electron is negatively charged, and the anti-electron neutrino is neutral. Notice that this answers the question we had from a long time ago about why this had to be an anti-electron neutrino and not just a regular electron neutrino. It's because of conservation of lepton number at this particular vertex. And you'll notice that in virtually every case, you stay within the generation. I believe, although I'm not sure, I believe that it's due to general conservation of energy considerations. But don't quote me on that. I'm not quite sure. In any case, you stay within the generation in this particular example. So I would know beta decay and be able to straight up draw it out very thoroughly because it is often asked about. Notice that this is beta minus decay. I will leave beta plus decay as an exercise to the reader. Notice that it is actually covered right here in this particular example problem, but I would encourage you simply to try it out on your own before taking a look at the solution. One more thing. This particular particle is mislabeled in the question, so just be aware of that.